Welcome to the Walton Pi. Today we're going to be talking about outer measures and Carathéodory's criterion. So an outer measure on a set X is a function mu star, which sends elements from the power set of X to the interval 0 to infinity inclusive. So we're allowed to take any subset of X, and it's going to be sending it to some number starting at 0 going all the way up to infinity inclusive, where we send the empty set to 0. If A is a subset of B, then the mu star outer measure of A is less than or equal to the mu star outer measure of B. And if E1 is, or if E1 through E infinity are some infinite collection of subsets of X, then the mu star of their union is less than or equal to the sum of their individual mu stars. Okay, so we say that a set A is mu star measurable if it satisfies the Carathéodory criterion, which is namely that for every test set T in our power set of X, that mu star of A intersect T plus mu star of T set subtraction from A is equal to mu star of T. So this is a lot to take in. So mu star empty set is 0. That just is a given if we're wanting to eventually turn this into a measure, which we are going to be able to do later. We need it to have smaller sets, have a smaller measure. And then we also want it to say, hey, if I take a union of countably many things, I want the outer measure of that to be less than or equal to the sum of their individual outer measures. And then the Carathéodory criterion is just something that we need in order for this to actually be able to turn into a measure. We're basically only going to be taking the mu star measurable sets to be able to turn that into a measure. And so this Carathéodory criterion, where A intersect T plus T minus A gives us the outer measure of T, that's going to be the key idea that we're going to need. So let's now talk about Carathéodory's theorem. So if mu star is an outer measure on X, we set M of mu star measurable sets, so that's those things that satisfy this Carathéodory criterion. The set of mu star measurable sets is going to be a sigma algebra, and the restriction of mu star to M is going to be a complete measure on X. So if we have an outer measure, you restrict it to the mu star measurable sets, that is going to be a measure, and even better, it's a complete measure. Let's go through the proof. So let's start by letting M be the set of mu star measurable sets. We're going to show that M is a sigma algebra by proving that it is an algebra that is also closed under countable pairwise disjoint unions. So to that end, we're first going to show that M is an algebra by showing it's non-empty, that it's closed under complements, and that it is closed under finite unions. So the empty set is in M, since for every test set T, mu star of T is equal to mu star of T intersect the empty set, so that's empty, plus mu star of T minus the empty set, which is T. So that tells us that M is non-empty, since the empty set at least is going to be an element. To show that complements are in M, let's fix some element A in our sigma algebra M. Well, we don't know it's a sigma algebra yet, but we're going to show that. So let's now fix T to be a subset of X. Then mu star of T is equal to mu star of T intersect A plus mu star of T minus A, since A is mu star measurable. And then note that T intersect A is T minus the set X minus A. And that T minus A is T intersect X minus A. So we can write mu star of T equals mu star of T minus X minus A plus mu star of T intersect X minus A, which is exactly what we need to be able to conclude that X minus A is mu star measurable, since it satisfies our Carathéodory criterion, so that tells us that X minus A is in M, so M is closed in complements. To see that M is closed under finite unions, it suffices to show it's true for the union of two sets, because if it's true for two sets, we can use induction to get any finite number of sets. So let's let A and B be in M, and let's fix T to be some test set. Then mu star of T is equal to mu star of T intersect A plus mu star of T intersect, or T minus A. And mu star of T is also equal to mu star of T intersect B plus mu star of T minus B. So since B is in M, the above equality is true for any test set T, So let's consider the test sets T intersect A and T minus A. We're doing this so that we can be able to construct exactly what we need for A union B. So mu star of T intersect A, that is mu star of T intersect A intersect B, plus mu star of T intersect A minus B, and mu star of T minus A is mu star of T minus A intersect B plus mu star of T minus A minus B, which we can rewrite as mu star of T intersect B minus A plus mu star of T minus A union B. So that means we can write mu star of T as mu star of T intersect A intersect B plus mu star of T intersect A minus B plus mu star of T intersect B minus A plus mu star of T minus A union B, which is greater than or equal to mu star of T intersect A intersect B union T intersect A minus B union T intersect B minus A, and then we add all of that to mu star of T minus A union B, and this first thing collapses down into, using some De Morgan laws and combining things, into mu star of T intersect A union B plus mu star of T minus A union B. So we don't quite have equality, but we do have this inequality that we're able to leverage and use. Okay? Since it's always true that mu star of T is less than or equal to mu star of T intersect C plus mu star of T minus C, in particular, it's true when C is A union B. So from here, we had one direction of an inequality. Here we have the other direction of the inequality, so we actually have equality. Thus, A union B is in our now algebra, and that tells us that N is going to actually be an algebra on X. To show countable additivity, which tells us that it's a sigma algebra, we're going to need to do the following. Note that if A intersect B is empty, then mu star of A union B is mu star of A plus mu star of B, since mu star of A is mu star of A union B intersect A. And then mu star of B is mu star of A union B minus A, since their intersection is empty. So we're actually able to get this countable additivity. So let's let AI be a collection of sets in our algebra, and let's let AI intersect AJ be empty for all I not equal to j. So we have this pairwise disjoint collection of sets. Define B to be the union from 1 to infinity of the AIs, and Bn to just be the union of the first n. Since M is an algebra, each Bn is in our algebra. Okay. Since An plus 1 is in M, for all t in X, if we choose T intersect Bn plus 1 to be our test set in the Carathéodory criterion, we get mu star of T intersect Bn plus 1 is equal to mu star of T intersect Bn plus 1 intersect An plus 1 plus mu star of T intersect Bn plus 1 minus An plus 1. This means that mu star of T intersect Bn plus 1 is mu star of T intersect An plus 1 plus mu star of T intersect Bn. Thus, we can inductively find that mu star of T intersect Bn is the sum from 1 to n of mu star of T intersect Aj. That means that for all n, mu star of T is equal to mu star of T intersect Bn plus mu star of Bn, which is equal to the sum from 1 to n of mu star of T intersect Ai plus mu star of T minus Bn, which is greater than or equal to the sum from 1 to n of mu star of T intersect Ai. So that part stayed the same, but now instead of subtracting off Bn, we subtract off more. We subtract off all of B. Okay, so we have that inequality. And since this is true for all n, that means that mu star of T is greater than or equal to the sum from 1 to infinity of mu star of T intersect Ai plus mu star of T minus B, which is greater than or equal to mu star of the union of all the T intersect AIs plus mu star of T minus B. And that tells us that B is measurable and B is in M. That means that N is closed under countable pairwise disjoint unions, so that tells us that N is a sigma algebra. And now we have to show that mu star restricted to M is a measure on M, and then also that it's complete. Since the empty set is an M and mu star of the empty set is 0, all that remains to show for this to be a measure is that if AI from 1 to infinity is pairwise disjoint, then mu star of their union is equal to the sum of their measures. So following the methods we did a little bit earlier, we get that mu star of t is greater than or equal to the sum from 1 to infinity of mu star of t intersect AI plus mu star of t minus b, which is greater than or equal to mu star of t intersect b plus mu star of t minus b, and this holds for all t in x. In particular, setting t equal to b, we get mu star of b is greater than or equal to the sum from 1 to infinity of mu star of b intersect AI plus mu star of b minus b, which is mu star of b intersect b plus mu star of b minus b, which is equal to mu star of b. So that means we actually have equalities all the way across. Therefore, mu star of b is equal to the sum from 1 to infinity of mu star of b intersect AI, and we have that it's a measure. To see that mu star restricted to M is complete, let's let F be an element of M with mu star of F equaling 0. If we fix E as a subset of F, then we consider T as a subset of X, because we need to show it's complete, so we need to show that the subset of something of measure 0 is measurable and has measure 0. Then mu star of T is equal to mu star of T intersect F plus mu star of T minus F, which is greater than or equal to mu star of T intersect E plus mu star of T minus F, which is greater than or equal to mu star of T intersect E plus mu star of T, which is greater than or equal to mu star of T intersect E plus mu star of T minus E. And that tells us that E is measurable and mu star restricted to M is complete. Thank you so much for watching. I hope this video was helpful in understanding Carathéodory's theorem and Carathéodory's criterion, as well as the concept of outer measures. If it was, please like and subscribe. It really helps me to keep making these videos. I hope you have a great rest of your day, and good luck with all of your math.